Calc 2, Integral Calculus, Module 2, Techniques of Integration. So we are now on Unit 2. This time we're going to try Algebraic Substitution. Again, I am your lecturer for this particular module. I am Engineer Guzman, co-presenting this subject with Engineer Angloan. Okay? So, on the last unit, we've discussed already the integration by parts, which is another technique of integration that is now mainly used wherein your functions or the integrand now contains functions of different types. So, it's either algebraic functions coupled with a trigonometric function, exponential with a logarithmic. Okay? That is one area wherein integration by parts is very good on. This time, algebraic substitution or the methods of substitutions that we're going to discuss focuses now on different types of problems, meaning they are now preferred when you are now solving different types of problems. So what type of problems are substitutions, or namely algebraic substitution is suited for? Okay, so let's see. For this particular unit, we must evaluate the integral of an irrational integrand by substituting a new variable to transform it into a rational integrable one. What do you mean by irrational integrand? So usually when you say irrational, these are numbers with exponents of fractions, or these are numbers of square roots, cube roots, and fourth root, so on and so forth. Okay, so according here, we are going to substitute a new variable to make the irrational integrand rational. So our goal here is to eliminate these exponents which are fractional. Take note of the term substituting. So if we're going to substitute a variable, we're going to replace it. Therefore, x becomes y or x becomes z. Okay? Subsequently, if you substitute x, the variable itself, by z, you must also substitute its differential dx by the differential of your substituted variable, or the variable you are replacing it with. So x becomes z, and then dx becomes dz. So that's very important. For a substitution to be complete, both the variable and its differential must be replaced with your chosen variable. Okay? Now in this particular problems, there are different cases wherein you now apply different types of substitutions, or wherein you now substitute different variables or degrees of the variable to get the correct answer. Okay? There are 5 cases, and we're going to discuss them one by one. However, out of all of the 5 cases, the most general one is case number 1. Okay? So when the integrand contains fractional powers of x only, okay, x only, not any binomial, just the term x only, use the substitution x is equal to z raised to n, where n is the least common denominator of the fractional powers of x. Okay, so this time our term or our function is simply x. Okay, and we are only going to substitute it with a variable that is z raised to n, n being now the LCD of the fractional powers of x. Meaning, there must be other terms, or there must be multiple terms with a base of x raised to, okay, fractional exponents of different degree. Okay, so let's have that in problem number 1. So this is a case 1 because we only see term x. Okay, so x is present, yes. We have fractional powers of x, yes. The square root of x can be rewritten as x raised to 1/2. The cube root of x can be rewritten as x raised to 1/3. Now, if we're going to solve this, try to solve this using the basic integration formulas, you cannot solve the integral because there will be no available basic formula to solve this type of problems. If you're going to solve this now using integration by parts, you're going to have a hard time looking for your du, for your u, and differentiating it to du, and looking for your dv, integrating it to v. Okay, so you might want to try algebraic substitution, because algebraic substitution comes to play when you now have fractional powers or irrational terms. So the goal of substitution is to replace these fractional exponents or these irrational terms with a rational term or a rational form. Okay, so according to case 1, if you have x, okay, so we do have x of different fractional powers, yes we do, so x raised to 1/2 and x raised to 1/3, okay, we might want to consider substituting x equal to z raised to n, z now being our new variable and n is now the least common denominator of the fractional powers of x. What are the fractional powers of x in our problem? That is 1/2 and 1/3. So going back to your basic algebra, what is the least common denominator for 1/2 and 1/3, or 2 and 3? So the LCD of these two is 6. Therefore, the LCD of 2 and 3 is now 6. We replace x equal to z, our new variable, with an exponent of n, the LCD of 1/2 and 1/3, which is 6. So we say, let x be equal to z raised to 6. This is where we begin our substitution. However, recall that when you are substituting a variable in a process or in an integration problem, you must also substitute its differential. Because if you replace x with z, you cannot integrate z with dx. You can only integrate z with dz. Therefore, to substitute dx, we simply differentiate x. So we say if x is equal to z raised to 6, therefore the differential of x dx is simply equal to the differential of z raised to 6. So that becomes, by the power formula for differentiation, 6z raised to 5 dz. Okay? So if you now have the substitute of x, of your variable, and if you now have the substitute of dx, the differential, simply replace them in your original problem. So this time, dx becomes 6z raised to 5 dz. So that is 6z raised to 5 dz. And what about the term here? So you're going to replace x with z raised to 6, correct? So if you replace x here, the square root of x, with z raised to 6, that becomes the square root of z raised to 6. X is equal to, or square root of x is equal to, x raised to 1/2. So if you substitute x equal to z raised to 6, that is z raised to 6 raised to 1/2. Therefore, it becomes 6 multiplied by 1/2, z raised to 3. You've now successfully eliminated the irrational term or the fractional exponent. Okay? Same thing with x raised to 1/3. The cube root of x, if x is z raised to 6, is now the cube root of z raised to 6. The cube root of z raised to 6 is simply z raised to 2. So this is now your substituted, okay, so take note, this is now your substituted expression. This is now a what? A rational integrand, correct? Because there is no longer any fractional exponent or a square root symbol, right? So can we now substitute this? Can we now integrate this? Yes, but with the help of factoring and some other methods, okay? So notice here at the denominator, z squared plus z cubed plus z squared. We can factor out z squared, so this becomes z squared z plus 1, okay? So the denominator. And then you notice you can factor out 6, right? 6, and then z cubed dz. This becomes cubed because z raised to 5 will cancel with z raised to z squared over z plus 1. Okay? Now what is this? This is now a expression that can no longer be, or that cannot be solved using what? The basic integration formulas. But what you can do is to divide first the numerator by the denominator. Now the division of terms is, you've already been doing this in differential calculus, correct? When you're now simplifying your differentials. Why are we dividing z cubed by z plus 1? Well, we divide it to make the fraction rational, okay? So we're going to have a discussions for improper and proper rational fractions as we go along the techniques of integration. But for now, if you divide z cubed plus z plus 1, you will now arrive with these terms. Now, how did you get these terms? Simply divide z cubed by z plus 1. The process, just recall it from your differential calculus, okay? So, dividing z cubed by z plus 1, you get z squared minus z plus 1 minus 1 over z plus 1, okay? Notice that these are now integrable on their own, correct? So, if we distribute dz, the integral of z squared simply is 1/3 z cubed. The integral of negative z is simply 1/2 z squared, and then the integral of dz, right, is z, and then the integral of this is negative ln of z plus 1 plus c. So is let's say multiplying 6, 2z cubed minus 3z squared plus 6z minus 6 ln of z plus 1 plus c. Is this your final answer? Absolutely not. Okay, so remember we are in algebraic substitution. To arrive with this particular answer, we had to replace the original variables, therefore also replacing the irrational terms with rational terms. But this is not the original variable of your problem. The original variable of your problem is x, correct? And since x is equal to z raised to 6, if you take the 6th root of z, we get the 6th root of x. Therefore, we can say that z is equal to the 6th root of x, or x raised to 1/6. Therefore, bringing back or substituting back, okay, the original variable to your answer, we get this particular final answer. And that is the essence of substitution. Substitute the original variable so that you can remove irrational terms. But then if you arrive with the final answer, you bring back the original variable. So this is not your final answer, okay? If you perform substitution, the final answer must still be in terms of the original variable of the problem. Okay? So remember that the original variable of the problem must come back on your final answer. This is case 1. This is probably the easiest one here in algebraic substitution because it only contains terms of x. Okay? For the particular or for the succeeding cases, it's a bit complicated or a bit more difficult because we're no longer only looking for x as the base. We're looking for the base as a binomial. Okay? So with that, let's have example or case number 2. When the integrand now contains fractional powers of a plus bx. So case 1, this is only fractional powers of x, correct? This time, the fractional powers are observed in a plus bx. What is this? A is a constant, it's a number, correct? B is a coefficient of x, is a factor or a number multiplied by x. This is now our base, okay? So this term will contain fractional powers. So the base is now a binomial, no longer x alone, okay? Use the substitution, this one. So instead of just x equal to z raised to n, we let a plus bx equal to z raised to n. N still being the least common denominator of the fractional powers of a plus bx. So again, we are looking for terms that is now, or terms with a plus bx. Okay? So for example number 2, we do have that term. Okay? So where are our terms? So remember, we're looking for the term a plus bx that has a fractional power. Okay? 4x plus 3 satisfies a plus bx because you can interchange this and it becomes 3 plus 4x. That's correct. 3 is your a, 4 is your b, but it does not have a fractional power. What does have a fractional power, however, is 1 plus 2x. It follows the form a plus bx, correct? And it has a fractional power. So it says on case number 2, if you have this, okay, if you have this expression a plus bx raised to a fractional power, you can replace it with z raised to n. What is n again? The least common denominators of these bases. The base or the exponent of this base is 1/2. Its LCD therefore is 2, right? So the least common denominator of 1/2, since it's a single fraction, is simply 2. So what do? We substitute a plus bx equal to z raised to n. Our a plus bx is 1 plus 2x, not 3 plus 4x, correct? Because 1 plus 2x is the one with the fractional exponent, okay? So we substitute a plus bx, that is 1 plus 2x, equal to z raised to 2, LCD of 1/2, okay? So if we do that, remember we are substituting x. Our goal is to replace x. Therefore, we must find or we must solve for x in terms of z. So transposing 1 to the right side, this becomes z squared minus 1. And then dividing both sides by 2, we get x equal to z squared minus 1 over 2. That is x. But remember, in algebraic substitution, we not only substitute the variable, but its differential. So if we're solving for the differential of x, we simply differentiate this equation. So dx, x becomes dx. And this becomes what? So 1/2 is a factor, so 1/2. The differential of z squared minus 1, so 1 is a constant, so 0. Z squared, that is 2z dz, right? So 1/2 times 2z dz, this simply becomes z dz. So we now have an expression for the substitution of x, and we now have an expression for the substitution of dx. So we can now replace the original variable of the equation of the problem with z. So to do that, So simply, what do we do this time? 4 times x, what is x? Z squared minus 1. So 4 times z squared minus 1 plus 3. Okay. What is this? 1 plus 2x, correct? Square root of 1 plus 2x. So 1 plus 2x. What is 1 plus 2x again? 1 plus 2x is equal to z squared, correct? So this becomes z squared. The square root of z squared is simply z, right? Simply z. And then dx is replaced with z dz. So the substitution is now complete because we've successfully eliminated or replaced variable x and differential x with z and dz. So just a process of simplification, and then we can now integrate. 4 over 2, that is simply 2. So 2 multiplied by z squared minus 1 plus 3, that's 2z squared minus 2 plus 1, correct? Z and z will multiply to each other, so that's z squared dz. I think you can cancel out negative 2 and 3. You can add negative 2 and 3, so this becomes 1, right? So 2z squared plus 1, quantity, z squared dz. Distribute z squared, so this becomes 2z raised to 4 plus z squared dz. These two can be integrated using the simple power formula, correct? So this becomes 2/5 z raised to 5 plus z cubed over 3 plus c. Okay, so this is now your integral. However, recall, this is substitution. Your final answer should not contain the substituted variable, or instead it should contain the original variable of your problem. If 1 plus 2x is equal to z squared, if you take the square root of both sides, we can say that z is the square root of 1 plus 2x. And substituting this expression to z here, we get our final answer as this one. As always, with substitution, the final answer must always be in terms of the original variable of the problem. Okay? Case 1, again, x is equal to z raised to n. Case 2, a plus bx is equal to z raised to n. Okay? You are looking for these terms with a fractional exponent. Okay? That is for example number 2. Now, case 3 and case 4, these are a bit complicated, a bit more different. Okay? Because they contain more conditions. Okay? So, for case 3, this one is a bit, or these two are a bit, let's say, a bit more difficult than case 1 and case 2. Okay? When the integrand contains the expression, okay, so when the problem contains this expression, x raised to m, an exponent, quantity a plus b, x raised to n, okay, x raised to n, closed quantity p over q, right, where m, n, p, and q are integers, okay, n, q are greater than 0, and if, okay, so this is the condition for case 3, if m plus n over n is an integer. When you say integer, this is now a whole number, okay? A whole number and not a fraction, okay? If this is a whole number, this expression is a whole number, then use the substitution a plus b x raised to n is equal to z raised to q, okay? So it's already a bit complicated, but if you know the condition, then it's simple substitution. However, for case 4, okay, case 4 is a corollary of case 3. For this one, if this does not become an integer, okay, if m plus 1 is not an m plus 1 over n is not an integer, then you might be looking at case 4. So for case 4, same scenario, same expression that we're looking for, okay, here. But this time, the term is m plus 1 over n plus p over q. If this is the integer, if this one is the integer, then we substitute a plus bx raised to n is equal to x raised to n z raised to q. Okay? So case 3 and case 4 are related to each other. They have the same, or we're looking for the same set of terms, but we're looking at, or they are considering different conditions. Okay? So let's try to solve an example for case 3 or case 4. Again, we're looking for this term, x raised to m, a plus bx raised to n, quantity raised to p over q. Okay. Let's have example number 3. Does example number 3 fall under case 3 and case 4? Let's see. So we have the integral of dx over x squared, fourth root of, okay, fourth root of quantity 1 plus x raised to 4 cube. So at first glance, this might not even belong to our case 3 or case 4. But if we try to manipulate the equation so that it follows the form x raised to m times a plus b x raised to n close quantity p raised to q, what do we get? Let's see. Okay, so x squared can be brought up. We can bring this up to the numerator. So the exponent becomes negative, x raised to negative 2. Okay, this, the fourth root is a fractional power of 1/4, correct? So 1/4 multiplied by 3, that is 1 plus x raised to 4 raised to 3/4. And if you bring it up to the numerator, it becomes negative 3/4. Does this follow our term? Yes. We have x raised to m. Our m is negative 2. We have the term a plus b x raised to 4. Okay, what is our a? 1. What is our b? 1 as well. What is our n? 4. Then it follows also close quantity raised to p over q. What is our p? Negative 3. What is our q? 4. Okay, so does this fall under case 3 or case 4? Yes. How do we know which case it falls to? Simply follow the condition. If it's m plus 1 over n is an integer, it falls under case 3. But if m plus 1 over n is not an integer, and if m plus 1 over n plus p over q is an integer, therefore it falls under case 4. If we try to do that, what is m? Negative 2 plus 1, that's negative 1. N is 4, that is negative 1/4. That is not an integer, that is a fraction. Therefore, it does not belong to case 3. So we simply check again. M plus 1 over n plus p over q this time. So this becomes what? 2 plus 1 over 4, negative 1/4, plus negative 3 over 4. Negative 1/4 minus 3 over 4, that is negative 1. Since this is an integer, we are now on case 4. So we follow case 4. So what are we going to substitute? This, a plus b x raised to n is equal to x raised to n z raised to q. Okay, not this one. This one is for case 3. Okay, so if we're going to substitute this one, what is our a plus b x raised to n? That is 1 plus x raised to 4. That is this one. Equal to x raised to n. What is our n? 4, right? 4. Z raised to, what's that? Q. What is Q? The denominator, that is 4. So z raised to 4. Okay? So this is our substituting expression. But we are substituting what? We are substituting x. We're replacing it with z. Okay? So solving for x in terms of z. So what do we do here? I guess we can transpose x raised to 4 to the right side. This becomes x raised to 4, z raised to 4 minus x raised to 4. Factoring out x raised to 4, we get x raised to 4 quantity, z raised to 4 minus 1. Dividing both sides by z raised to 4 minus 1, we get x raised to 4 is equal to 1 over z raised to 4 minus 1. And then taking the fourth root, correct, of x raised to 4 or both sides, that is the same as raising it to 1/4. We get x finally as 1 over z raised to 4 minus 1. Or if we bring up the numerator, or we bring up the denominator here on the numerator, we simply take the negative exponent. So this becomes z raised to 4 minus 1 quantity raised to negative 1/4. This is now x. So we can now replace x. But remember, in substitution, we also replace dx. Okay? So take the differential of this expression. This is simple by power formula only. So dx is n negative 1/4 quantity u raised to n minus 1, correct? So z raised to 4 minus 1 raised to negative 1/4 minus 1. Negative 1/4 minus 1 is negative 5/4 times, what is this? The differential or the derivative of the term inside, z raised to 4, that is 4 z cubed dz. Okay? Simplifying, I think 4 will cancel out with 4. Therefore, you get negative z cubed multiplied by z raised to 4 minus 1 raised to negative 5/4 dz. Okay? This is now your dx. If you now have an expression for x, z raised to 4 minus 1 raised to negative 1/4, and an expression for dx, negative z cubed multiplied by z raised to 4 minus 1 quantity raised to negative 5/4 dz, substitute this to the original problem, and we have now this. So it's a bit much, right? So cases 3 and cases 4 are a bit much for substitution. But if you have a good background in algebra, in simplification of terms, then this should not be a problem at all. Okay, so we're going to substitute x squared. X is this, square it, correct? That's it. dx, this is dx, that is dx. This is what? Fourth root of, okay? Fourth root of, or raised to 3/4 of 1 plus x raised to 4. What is 1 plus x raised to 4? And that is this one. But we're looking only for z. Our goal is to substitute only z. So that is 1 plus x raised to 4. X raised to 4, that is this one. Raising it to 4, correct? Raising it to 4 there. Okay? And then raise everything by 3/4 because the fourth root of a cube is raised to 3/4. Okay? So can we now simplify? Yes, but slowly but surely, right? We can factor out -1. -1 can be outside. So no more negative sign here. What about here? Here we get 1/4. Okay? So 1/4 multiplied by raised to 2. That is 2/4. So 1/2. Correct? But that's still on the denominator. So if you bring it back, if you bring it up, it becomes raised to -1/2. Okay? And then plus, this is simply 1/4 raised to 4. That is simply raised to 1. Okay? So remove this, these two. This just becomes 1 plus, okay, 1 over z plus 4, raised to 4 minus 1, raised to 3/4. So let's continue the simplification. So here, so from this one, okay, we now cross multiply, or we now combine the fractions. Okay, so cross multiply 1 and z raised to 4 minus 1, that becomes what? Z raised to 4 minus 1 plus 1 over z raised to 4 minus 1. Again, this becomes cross multiplication because the LCD of this is 1. So the fraction becomes z raised to 4 minus 1 times 1. Okay, the denominator. So cross multiplying, again, this becomes 1 times z raised to 4 minus 1. So the numerator becomes z raised to 4 minus 1 plus 1 over z raised to 4 minus 1. So -1 plus 1 cancels out. So it gives you only z raised to 4 over z raised to 4 minus 1. Okay? Can we simplify further? Yes. Okay? We can factor out, or we can distribute the exponent of 3/4, the numerator here and then here. So z raised to 4 raised to 3/4, that is z raised to 4 times 3/4. So you cancel out 4, it becomes z raised to 3. Okay? And then z raised to 4 minus 1 raised to 3/4. If you bring it up to the numerator, it becomes z raised to 4 minus 1 raised to -3/4. So this is your expression. Can we cancel something else? Oh yes, we can cancel what? We can cancel 1/2. Oh wait, z raised to -1/2 and z raised to -3/4. Okay? So what is this? So if you combine these two, you need to add their exponents, correct? So the LCD, if you're going to add -1/2 and -3/4, that is 4, correct? So this can be rewritten as 2 over 4. This can be rewritten, this is -3/4. So -2/4 minus 3/4, that is -5/4. Okay? So that is here. So if we simplify that, notice that z cube on the numerator will cancel with z cube on the denominator. Z raised to 4 minus 1, quantity raised to -5/4, will cancel with z raised to 4 minus 1 raised to -5/4. Okay? Therefore, leaving us only with integral of dz. Yeah? After all of that simplification, we're only left with the integral of dz. So much for effort, right? But still, if you have a wrong simplification from this, you will not arrive with this. Again, did you get this one? Okay, so we're adding base of z raised to 4 minus 1 by their exponent. So if you multiply these two, correct, by index laws, exponent laws, you're going to add their exponents. -1/2 minus 3/4. 1/2 can be rewritten as 2/4, so that they have the same denominator. So -2/4 minus 3/4 is -2 minus 3, -5/4. That's why we had the same exponents. Okay, so we now have dz, and the integral of dz is simply z. Okay, is this your answer? Of course not, because you need to bring back the original, okay, variable. So what is z equal to? From this one, what is z equal to? So dividing both sides by x, that is 1 plus x raised to 4 over x raised to 4, and then taking the fourth root, we get this expression. Okay, So bringing it back, we get the final answer. Okay, that is for case 3 and case 4. However, I don't really suggest, okay, or these type of problems are already the difficult problems. Okay, so you might not really encounter them much, especially if we go now to the applications of integrations, or when we now go to definite integral. But okay, it's still a good practice to have all of these techniques available or ready for you to use. Okay, that is example number 3. We do have one more case, that is the reciprocal substitution. Okay, it says here that some irrational integrand may be simplified by letting x be equal to 1 over z. Okay, so this one's a bit simpler. We're not going to look for particular terms. We're just simply letting it take the reciprocal of our original variable. So let's take our favorite example number 3, and this time solve it with the reciprocal substitution. Okay, so here on the reciprocal substitution, we're not looking for any terms. We're not looking for a plus b x raised to n. Okay, we're just simply saying, okay, what if we try substituting now x to a reciprocal function? Let's say x is equal now to 1 over z. Okay, so let's just try it. Let's see what will happen. If x is equal to 1 over z, therefore dx is equal to dz over z squared. Okay, negative dz over z squared. Much shorter already, correct? So we now substitute x and dx on your original problem. So what does this do? Dx is equal to negative dz over z squared over, what is this? X squared, what is x? 1 over z. So that's 1 over z quantity squared. Okay. The fourth root again of a cube is raising it to 3/4. So that becomes 1 plus 1 over z raised to 4, correct? Quantity raised to 3/4. So simplifying, let's factor out the negative sign. Factor out the negative sign here. That's 1 over z squared, okay? That is 1 plus 1 over z raised to 4 if you distribute the exponent, and cross multiplying z raised to 4, z raised to 4 plus 1 over z raised to 4. Okay? Can we simplify something here? Yes. So if we distribute 3/4 the exponent to z plus 4, z raised to 4 plus 1, it becomes z raised to 4 plus 1. If we distribute 3/4 the exponent to z raised to 4, that is z raised to 4 times 3/4. Okay, I'm talking about the exponent, okay? Z raised to 4 times 3/4. So 4 times 3/4 becomes z cubed. Okay, and notice here, z squared will cancel out with z squared here, since they are both on the denominator of the respective complex fraction. So it will cancel out, leaving you with only this, negative dz over z raised to 4 plus 1 raised to 3/4, correct, over z cubed. Can we bring this back to the numerator? Yes, so simplification, right? Z cubed can be brought up to the numerator, and it's positive, okay, because it's on the denominator, right? So in dividing fractions, remember, you multiply the numerator by the reciprocal of the denominator. So this is your denominator, this is your main fraction bar. So this becomes z cubed dz over z raised to 4 plus 1 raised to 3/4. I think this can be solved using the power formula. Let's see. If we bring this up to the numerator, it becomes z raised to 4 plus 1 raised to negative 3/4, okay, z cubed dz. If this is by power formula, we let u be equal to z4 plus 1. We let n be equal to negative 3/4. What is du? That is 4z cubed dz. We're missing 4, so we need to introduce a balancing factor of 1/4. Does it satisfy the power formula? Yes. So performing power formula, our balancing factor here, okay, multiplied by u raised to n plus 1, negative 3/4 plus 1 is 1/4 over n plus 1. So we get this expression. Simplifying, these two will cancel out, so we simply get equal to negative z raised to 4 plus 1 raised to 1/4 plus c. This is not, of course, our final answer. We need to bring back the original variable. If x is equal to 1 over z, therefore z is equal to 1 over x. And simplifying, okay, 1 over x raised to 4, this becomes the final answer. Same? Yes, same with case 3 and case 4. Okay, so you choose which one do you prefer. Okay, but I think the reciprocal substitution has a shorter solution and requires fewer conditions. But not all problems, okay? Not all algebraic substitution problems can be solved using reciprocal substitution. So it's up to you to discern which one you're going to use, okay? And that's it for algebraic substitution. So you might want to try this one, okay, on your own, okay? The integral of dx over x, square root of 4x minus x squared, okay? So you can try this one on your own. And that is it for algebraic substitution. So remember, irrational integrands, which seems impossible to be evaluated, can be transformed by using other variables but should always be eliminated by substituting back the original one. Okay? Again, irrational integrands, those are your square roots, cube roots, your fractional exponents, can be solved using substitution. Reciprocal substitution is not only limited to a specific form of algebraic integrand as long as it will make the function simpler and integrable, meaning this might be available for you in trigonometric function. So you try to explore on that one. Okay, so that is it for algebraic substitutions. There are still a lot of techniques of integration that we still need to discuss, so kindly wait for those. Okay, so again, if you have any questions, you just write them on our chat box in Canvas or our official company email. Okay, and with that, thank you.